Today on Applied Science, I'm going to talk about designing and creating small batches of glass. This is an unusual branch of engineering that's very unlike electrical or mechanical in that there's basically no information available how to get started in the home shop. So today I'm going to summarize everything I've learned in the last couple months, including reading out of print books and talking to glass experts, and show you how to start having fun with this right away. Okay, so let's check out some demos. Let's take a look at this unusual piece of glass. I'm going to shine some light on it from this blue laser pointer that I got from eBay. Let's see what happens. As you can see, the glass is actually changing color when I shine light from the laser pointer in there. And it's fairly responsive. It changes in a few seconds. This glass is actually photochromic, so it's basically the same kind of glass that is used in sunglasses that change color when you go out into the sun. And some regions of it are a little bit more sensitive than others, but you can definitely see what's going on here, right? Let's try this one. This one's also photochromic. We can also give it a blast of light from this really big ultraviolet flashlight that I have here. Let's try this one out. This is about the same wavelength, 405 nanometer, as the laser pointer. It's just more of it. There's more LEDs in here. And then just for comparison, this is like a modern photochromic lens that these guys donated to the channel a long time ago, just so you can see the performance difference. So a modern, this is actually a plastic lens, and so it's not quite the same chemistry in here, but you can just get an idea of of how it works with a modern photochromic lens with dyes in plastic as opposed to glass. And now all of these are actually reversible, so if we wait around long enough, both the commercial lens and the glasses that I've created are, they'll eventually go all the way back to their original state. Now in the commercial lens this happens in hopefully 5 to 10 minutes. In the glasses that I've created, it's quite a bit longer. I could time-lapse this, but it's really kind of like an overnight thing for this to translate back to its original clarity. Pretty cool though. There's nothing special about this laser pointer. I'll put links to everything as always in the description. You can go on eBay and just pick up one of these laser pointers. Okay, so that's this actually, making this piece of glass took a long time, let me tell you. Most of the samples that you've seen on this table here were me attempting to make photochromic glass. And it's taken a long time because there's a lot of variables involved here. And I'm very happy to get this level of performance. So this is not anything shocking. I mean, this has been around since the 1950s or 60s. However, I'll bet you have not seen a piece of glass that works quite like this one. This one is also photochromic, but as you can see, the fade time is just seconds. And so if I go across like this, you can see it's there, and then it fades. This is actually an opal glass, and so it is a piece of glass. It's just, it's not transparent. And it has this really weird property where you can draw on it and then it fades away almost instantly, just a few seconds. And the top has this weird kind of crystalline thing going on, but it also works about the same way almost. Unfortunately, this was a batch of glass that I made just by throwing a bunch of leftovers together in a pot. So the formula for this one's unfortunately lost to time forever. But the point is that I want to get everyone into hacking glass, because with, you know, as many people hacking on electronics and mechanics, if they were all hacking on making glass, we would have all kinds of weird stuff by now. So let's start talking about how to do this. When I first got started with this project, I thought what I would do is get a mold, a glass mold, dump all the ingredients in there with a mold release, heat it up, cool it, and then pull out my finished piece of glass. However, it can never work that way, unfortunately, and the reason is that the glass batch, when it's being formed, like going from a mixture of powders into a finished piece of glass, is extremely reactive, and all of the mold releases that you can put in here will actually get sucked up into the glass batch, and then you won't have a mold release anymore. There's only one material on Earth that won't stick to melting glass or forming glass, and that's platinum. And so they actually make tiny little platinum crucibles for doing laboratory glass analysis, but that's a little expensive, and apparently, from what I've heard, even then, the glass doesn't just fall out. I mean, it still sticks in there, and so if you're hoping to make like a nice, you know, good-looking puck of glass, it's not going to work forming it in a mold like this. So I'll just cover the mold releases quickly. if you do make a custom blend of glass and then you want to form it into an interesting shape, then you can use these conventional mold releases. And most of these things came from like an art supply house for glass artists. Two popular kinds of mold release are this Primo primer, and this is a powder in here that you mix with water, and it ends up making this fun purple solution. And the purple is actually a useful thing. When you're brushing it on your mold, you can tell the spots that you haven't covered because they aren't purple, so that's the point of that. And then I also tried this really expensive Boron Nitride mold release. This is actually really great stuff. It's also $50 a can. And it works really well, but again, if you're making glass, the temperatures are really high and the glass is very reactive, and it will actually suck the mold release into the glass batch, and that's actually what's happened here. So this was a mold that I coated with that boron nitride spray, and I put my ingredients in here, and what happened, this brown color is actually the boron nitride that's been incorporated into the glass. And then after the glass was done eating away all of my mold release, it proceeded to stick itself permanently to the mold, which is alumina. So what happened here is I basically just glazed the mold. I started with this unglazed piece of alumina, and now the glass is permanently fused in there. So the way to do it is to get a melting dish, and I'll put links again to all this stuff. These you can actually buy these on Amazon. They're a little expensive on Amazon. If you get these imported, you know, from a Chinese seller on eBay, it's just like $1 or $2. I mean, it's no big deal. And you can take these up to very high temperatures, and what you want to do is put your glass batch in here, heat it up, and then pour it out onto something else. We'll get into the details later. Also, I should point out that you might have heard of float glass. So commercially, if you want to make like a big sheet of glass and make sure that it's really flat, what can you do? You don't want to put it through rollers because the rollers, you know, might mar the surface, or you'd have to adjust them to make them really parallel. So the way that glass is made commercially is a giant vat of molten tin, and they pour the molten glass on top of the molten tin, and because gravity makes things flat at the small scale here, you're guaranteed that everything will be flat and uniform because you're dealing with liquids. It's like the surface of a lake, right? It's going to be flat. There's a couple of interesting so I tried it, of course. Inside here I've got some tin. I bought tin pellets on eBay and put them in my crucible here and melted it, and then put some glass on top, and you can see it kind of almost worked, but there's a couple of interesting problems. One, the tin oxidizes if you just heat it up in air. So commercially, what they do is have a giant furnace full of hydrogen gas where this liquid tin is hanging out, and the hydrogen gas is very reducing. It basically prevents oxygen from being in there, because if any oxygen got in, it would react with the hydrogen. So needless to say, this is getting to be kind of difficult to do in the home shop, having a molten tin with hydrogen gas and everything. And then another interesting problem, if you're making photochromic glass, for example, you can't do it in the float glass process because this glass is very sensitive to the environment it's in. And it really doesn't like hanging out in a hot hydrogen environment because it actually prevents the glass from being photochromic. So this can only be formed in crucibles or in oxidizing environments. You can't use the float glass process for this. So originally when I was having this problem with the glass sticking to the molds and I was wondering what to do, I thought, well, maybe I'll try this liquid metal idea, since how could it stick to liquid metal? And I would recommend not bothering with this at all. As it turns out, if you want to make a flat piece of glass in the home shop, there's easier ways to do it. Just forget the tin. It's actually not that helpful. If you're in a bind and you can't find or afford these alumina melting dishes, it's also possible to use porcelain. So if you go to the store and buy, you know, dishware, just plain old porcelain dishware, this can be okay. The temperature that this can sustain is just barely high enough to do some glass experiments. And we'll get about, you know, we can talk about making the glass melt at low temperature so that you can use porcelain melting stuff. The one thing you have to be careful about is that if you buy dishware from the store, it's already glazed, right? So there's already glass inside here on top of the porcelain, and you can feel the difference. Like if you touch this part of it, it's typically not glazed, so that's the raw porcelain, and then inside it's already covered with glass. So if you're making a glass batch and you pour all your ingredients in here, it's going to be mixed along with whatever glaze the manufacturer already used. Whereas if you go with one of these unglazed melting dishes, this is really raw. There's nothing that this is going to contribute to your glass batch, or it's the minimal amount. Okay, so you've got your aluminum melting dish or your porcelain demi-tasse, and you're ready to put it in the kiln to melt all the stuff down. So let's talk about kiln selection. First, gas versus electric. In this tabletop small scale size, there are no commercial gas kilns, so you'd have to make one, but that's not the end of the world. There's a couple other considerations though too. You want your kiln to have really good temperature control, like plus minus 10-20 degrees C, because a lot of making unusual kinds of glass involve heat treatment and annealing, and you really do need good temperature control to do this. So, really fine temperature control with a gas kiln is more difficult. You probably need to throttle the gas down, not just turn it on and off to get good temperature control. But the last consideration, and sort of the most difficult one to get around, is the atmosphere inside the kiln. Remember I was saying that having hydrogen atmosphere is no good for photochromic glass because it would actually chemically hurt the glass and prevent it from being photochromic. If you have a gas-fired kiln, the exhaust from your flame is actually reducing. There's probably quite a lot of carbon monoxide in there. And at these temperatures, that carbon monoxide will find oxygen molecules and react with it to make carbon dioxide. And it's so reducing at these high temperatures that it will actually pull oxygen out of the glass and prevent it from being photochromic. So I don't know, I think commercially you could probably get around this by having a really big crucible inside your gas-fired kiln, and it's only the surface layer that's affected by the reducing atmosphere in a gas-fired kiln. The trouble is, if you're using small little melting dishes like this, the amount of surface area up here is high enough where if you've only got 100 grams of glass in here, it's basically all going to be affected by the atmosphere in the kiln. So using an electric kiln is very nice because temperature control is much easier, and if you open the lid to the kiln, you're guaranteed to have atmospheric air inside there. And later on you'll see there's so many variables involved with making a piece of glass that eliminating one more variable of having this unknown atmosphere from a flame in your kiln is another thing. Especially if you're turning the flame on and off to control the temperature, now you're controlling also the oxygen level because the flame is on and off, and so then there's more or less oxygen. I would recommend definitely going with an electric. This particular kiln here is called a muffle kiln, and it's built kind of funny. It almost seems like a DIY project itself. It's basically just this helmet-shaped thing, and then you can see the heating elements inside there, and you can put it down on any surface you want and sort of turn that into a kiln. This is the Paragon Quickfire. I bought this a long time ago. It's not sponsored, of course. This is about $300 new, I think, and it's actually a really good solution. The heating elements are rated to go up to about 1050 degrees C, but I've pushed it to 1150, no problem. One consideration is that it just comes with a switch. So the original temperature control is a switch that you turn on and off yourself, and an analog temperature gauge here to tell you how hot it is, and that's not going to work for doing glass heat treatment or annealing. So what I did is I added this little PID controller here, and you can set the temperature, and it's actually amazingly good at reaching a temperature and holding it within just a few degrees even. The reason that this kiln is limited to maybe 1150 C or even 1250 if you really, really push it is because the heating elements themselves are made of nickel iron, right? Nichrome. And eventually it melts. So it's a pretty hard limit on how hot you can get it because your heating elements eventually get so hot they melt. So that really does put a cap on things. And unfortunately most silica glass batches have a rated melting or forming temperature of 14 or 1500 degrees C, which is much too hot. You'd never get your nichrome furnace that hot. So what do? Well, there are actually special electric furnaces that have heating elements that are not made of nichrome. So the next level up from nichrome is silicon carbide. It's actually conductive and it melts at a higher temperature, so they make heating elements out of that. And then the top of the line is molybdenum disilicide. Very unusual material that's a blend of molybdenum and silica. And they make these very, very expensive small heating elements out of this material, and you can get a kiln, an electric kiln, that goes up to 15 or 1600 degrees C. The downside is that these kilns are really expensive. Even, you know, cheap import models on eBay sell for like $2,000 or $3,000. So, you know, it's, in the context of this video, it's really just kind of out of reach. I wouldn't worry about it. The nice thing is that you can make glass formulations that just don't require that kind of temperature. So there's lots and lots of experimentation you can do without bothering with any of that, and that's what we're going to talk about in this video. This kiln originally came with its own shelf, like its own bottom, and you can see what happened here. Now remember I said that glass is very reactive, so if you spill a little bit of glass batch on the shelf here and then heat it up to high temperatures, it's actually dissolving away the material of the kiln itself. So you have to protect the kiln and everything in there from your glass even. Now, spilling it is actually a very damaging, like corrosive kind of event. So luckily this material is not super expensive. And the nice thing about these muffle furnaces where you sort of pick the whole furnace up is that you can just have like a new bottom every month or whenever you need it. So you can buy these fire bricks that are very lightweight and can take very high temperatures and are also insulating. So I'll put links to all this. If you search for fire brick, be careful, because some fire bricks are rated for high temperature, but they aren't really insulating. Like it can withstand fire, but it's going to get hot on the other side. Whereas a brick like this, it could be, you know, 1400 degrees C on this side, and you could put your hand on this side and it would be no problem. So to repair this kiln, what I did is I just put 2 of these standard size insulating fire bricks here, and that's now my kiln floor. Another thing you can do to try to promote the life of your kiln floor is to cover it with this special kiln paper. So they sell this stuff at the art supply stores, and watch how it works. Pretty cool. It's paper that doesn't really burn. And so if you put glass on top of here, this acts as sort of like a buffer layer, and this will eventually become completely white ash, and the glass won't be able to stick to the kiln floor because there's this layer of ash in between. So pretty handy stuff. Just keep in mind though that if you pour your glass batch, like if there's powders on here that are going to form a glass, they will dissolve the paper and the ash and everything else like we mentioned and eventually get all the way through. So this is sort of a low-level way to protect yourself from spills. You can see in my kiln here, there's all kinds of remnants of ash here since I've been putting kiln papers on here to try to protect the top. Not 100% though, because you can still see little errors here and there. Oh, also, you can use sort of a trivet. So what will happen is the glass is very viscous and sticky, and so if you've got your melting dish like this, eventually you'll get some running down the side here. It'll dribble down, and if it's just sitting on top, even with the kiln papers, it'll eventually make a huge mess and destroy your kiln floor. So you can put like a porcelain or alumina tray here so that when you put this down, the drip is at least caught by that. You can keep the kiln floor living a little bit longer. So we talked about making your glass batch in an alumina melting dish like this and then pouring it out onto a surface. There's actually a really great material for doing this, and that's graphite. So if you go on eBay or Amazon, you'll find there's these graphite casting molds, mostly for metal actually. They weren't thinking that you would use this for glass, but you can. And what I've found to work really well is to get a mold of about this size and put it down like that. You can use sandpaper to get the surface really flat and then use like a paper towel to polish it. And then when you're getting ready to pour your glass, what you do is you heat the surface up with a torch till, you know, it's maybe a few hundred degrees C or maybe even 500. And then obviously this is going to be hot. Open the kiln up and take your glass and pour it out onto the surface. And the nice thing is that the graphite will not stick to your glass hardly at all. I mean, it's a really slippery surface. What I found out doesn't work, don't do this, don't take the whole thing and put it in your kiln and then close the lid and heat the whole thing up to kiln temperatures. The graphite will survive, but what will happen is the glass will rip off the top layer and again incorporate the graphite into the glass because it's so reactive, so that doesn't work. Okay, so we've talked about the melting dish, the kiln, the mold release, and everything. What do we actually put in the dish to make this glass? This is where things get really weird. So if you search for patents about how to make weird kinds of glasses, let's say photochromic glasses, you'll find lots and lots of very detailed glass analyses, right? So you'll typically see, let's say you find a glass analysis, it's 50% silicon dioxide, 40% boron trioxide, 10% sodium oxide. Great, I'll just get 50 grams of silica, 40 grams of borate, and 10 grams of sodium oxide and mix it all together and make a glass, right? Not even close. The ingredients that go into the glass batch do not have a whole lot to do with what comes out the other end. And this may seem very strange, but there's a really great analogy, and that's in cooking. So if you analyzed a piece of cooked bread, you would say it's 20% gluten, 20% water, whatever it is. But if you were explaining how to make a loaf of bread to someone, you wouldn't use those terms. You would say start with flour and water. And it's actually the process of making the bread that develops it into gluten and all the other finished products. And that's exactly what's happening with the glass. One trick with making these glass batches is that the temperatures are so high that almost any carbon is going to go away. It's going to react with oxygen and leave the glass batch entirely. So if we, for example, put in lithium carbonate, when we heat this up to 1200 degrees C, the CO3 is going to go away, and the oxygen is going to, some of the remaining oxygen is going to react with the lithium, and we'll be left with lithium oxide in the glass. So, and then you may say, well, why not just start with lithium oxide? The problem is that lithium oxide is really reactive, and so if you put that in the glass batch, it's very possible that as the thing is heating up, all that lithium oxide is also going to go away before it has a chance to be incorporated into the glass batch. So choosing ingredients to make a glass sort of requires you to find an ingredient that has a melting point and a stability that is compatible with all the other materials in the glass. Luckily, a lot of this work has already been done. So if you sit down and you want to put lithium in your glass, you pretty much use lithium carbonate. There might be a few other chemicals that work too, but pretty much it's always lithium carbonate. And also, for example, if you want to add sodium to your glass, pretty much using sodium carbonate is the way to go. Okay. Unfortunately, there's not like a master table or anything that I've found that lists all the possible things you can put in. I mean, there's literally hundreds. It goes on and on. But to make sort of more normal kinds of glass, it is pretty well figured out, and I'll put as many links as I can in the description to help you out. When you're just starting out and making a relatively simple kind of glass, just plain old clear glass, I would recommend doing 20 grams of silicon dioxide, 20 grams of sodium carbonate, and 20 grams of boric acid. And this will make you a borosilicate glass. You've probably heard that term before. It's the same kind of glass that's used in glassware and cooking dishes and all this kind of thing. One benefit of borosilicate glass is that it is less sensitive to temperature fluctuation, right? Like you don't want your glass to crack if you're heating up a test tube or something like that. And similarly, if you're making glass on your own, you actually don't want it to be very temperature sensitive because you're going to have to cool your piece of glass down from kiln temperatures all the way to room temperature. And annealing is the process where you pick a temperature and hang there for a while to let the glass relax and sort of all the stresses dissipate. And it typically takes hours for this to happen. But having borosilicate glass, you still have to anneal it, but it's less sensitive than a non-borosilicate glass or something that's more sensitive to temperature fluctuation. Mixing up all the powders is pretty important, and it's something that I haven't spent a huge amount of time on, but I probably should. What I typically do is just have the container on the scale, put all the powders in it, and then sometimes I'll add these two brass balls and put the container lid on and shake it around. And the balls will help sort of stir up the powder and actually kind of crush some of the crystals a little bit to mix it up. In reality, this could be a lot better. I mean, what you really want to do is put it in a rock tumbler and run it for a day or an hour or something like that. And that will make sure that the powders are really, really well mixed together. And this is important because like we were talking about, the glass batch doesn't just sort of all melt together. It's actually a chemical reaction that's happening in there. So you really want the powders to be in really, really well-mixed, intimate contact with each other so that the chemical reactions can proceed as smoothly as possible. If you've got a clump of something off in one corner of the crucible, it's possible it will eventually melt and make a glass for you, but it may not have the properties that you want because it didn't properly react with all the other ingredients. And again, think of a loaf of bread, right? Like if you have a little chunk of unmixed flour or something in one corner of the pan, yeah, you'll still end up with a loaf of bread or something, but it's not going to be as good. And funny enough, the analogies with cooking continue. This is actually a good ingredient to put in your glass. Just plain old table salt will add sodium and chloride, and both of those are actually important in making photochromic glasses. And so it's no joke that, if your soup isn't very good, what do? You put in a pinch of salt. Same can be true of your batch of glass. The main components of the glass are not super sensitive to variations in ratio. So for example, if your glass is half silica and about half borate, getting it to be 49-51 isn't going to make any difference. But when you're making glasses that are photochromic or have like a very sensitive chemical aspect to them, some of the ingredients are very sensitive and the quantities are just absolutely tiny. So for example, in the photochromic glass, this copper oxide needs to be added about 0.08%, I think. And so measuring out such a teeny amount, even with a balance that's capable of measuring milligrams, is very challenging. So what you do is you dilute the sensitive ingredient in one of the base ingredients. So for example, for this borate glass, I'm using boric acid as like the main batch component. And so what I would do is take half a gram of copper oxide and mix it with 20 grams of borate. And so I'll have this very dilute sort of copper oxide powder. And then you can measure this out with also still pretty good precision, but not quite the precision that you need to measure the oxide by itself. Let's finish up by talking about the actual chemical ingredients that go into this photochromic glass, sort of as an example, and I'll try to describe and generalize what these ingredients do. So this winning combination that I've got here, this photochromic glass, has this recipe. It's 22B, and as you can see, I've spent a long time tweaking different components of the recipe. There are a lot of variables involved here. Not only is the ratio of ingredients important, but also the speed at which you bring them up to the melting temperature in the kiln, and then how long you hold it at that temperature. And then when you pour it out of the kiln, you let it cool down to room temperature and then bring it back up to a forming temperature to actually create this photochromic property. And then of course that has a time and temperature associated with it as well. And the atmosphere in the kiln during the melt process, and then the atmosphere during the heat treat process, and it just goes on and on. So I'm not claiming that this is tweaked down to perfection. In fact, far from it. This will just give you an idea of what's going on and sort of the challenges that you'll encounter if you end up doing this. I should also point out that a lot of the patents around photochromic glass talk about a lot of these times and temperatures, but they'll say things like, oh, the heat treatment may be conducted between 500 and 700 degrees C for between 10 minutes and 2 hours. Now, what will actually happen is that the heat treatment only works between 600 and 620 degrees, and it must be between 30 minutes and 40 minutes. But of course, they want the patent to be as broad as possible, and if there's some weird way you can make it work outside those parameters, then fine. But they're definitely not describing the easiest way to make it. They're describing all the possible ways to make it. And so that's kind of another problem with the patent system, is that it's you write them to be overly broad. But anyway, okay, let's get down to business here with the chemicals. This winning combination is a borate glass. There's actually no silica in it whatsoever, so it's not borosilicate, it's just boro, or borate glass. So we've got 20 grams of boric acid. This will contribute B2O3, or borate, in the final glass, and this is kind of the backbone of the whole system. Then we have 2.2 grams of aluminum hydroxide. Now remember, the hydrogen is going to go away at these high temperatures, and we're going to be left with Al2O3, so alumina, which is dispersed among the mixture. And the function of alumina is just to stabilize the glass structure. We don't want it to devitrify, which means convert from a glass into a crystalline structure, and this helps with that. This ingredient also calls for calcium carbonate, which again, the carbonate is going to go away, and this is going to become calcium oxide in the final glass. And this is also a stabilizer that makes the glass less dissolvable, like less prone to being broken down by the environment. I know that sounds silly for a glass that we only care about, I just want this to work in the lab. I don't care if this survives for years and years. But again, I was following a recipe and I got this thing locked in and I couldn't change this variable easily because I was too busy changing other variables, basically. Then we have 0.4 grams or 0.3 grams in the winning mixture of silver nitrate. This is actually the same chemical that works in old-fashioned black and white photography, and it's actually the same mechanism inside the photochromic glass. So what happens is we mix silver nitrate with sodium chloride in this glass mixture, and then as it's reacting, as the glass is being formed, these things trade places and we end up with silver chloride and sodium nitrate, and the sodium nitrate gets burned down into sodium oxide, the nitrate goes away, and we're left with silver chloride. And I have a little bit of silver chloride over here. Let's take a look. We zoom in. So there's some silver chloride, and if I shine this ultraviolet light on it again, check out what happens. Look at that. It turned dark, just like the photochromic glass. So basically, we're just dispersing this silver chloride throughout the glass, and that same process that you just saw is happening in the glass, which causes it to darken. The reason that it becomes dark is because the silver chloride, when it gets hit with this moderately high power light, it's not quite ultraviolet, but it's pretty close, it actually converts into metallic silver, and so that dark color is silver metal as opposed to silver chloride. So if we had a glass that changed from clear to dark only once in its whole lifetime and never went back to clear, it wouldn't be that useful as a pair of sunglasses. So we add another ingredient, copper oxide, in a tiny quantity. I've written down 0.1 grams, but this is actually a 40x dilution. So we're really only talking about 2.5 milligrams of copper oxide for this whole batch of glass. It's considered a dopant because it's in such small quantity. And what happens here is that it accepts electrons from the silver chloride. So when you hit the silver chloride with light, it converts to metallic silver and I think gives up an electron. Don't quote me on that. And then the copper oxide accepts that electron and then pushes it back into the silver metal, causing it to go back to silver chloride. So this is sort of like a reserve of electrons. And copper oxide has the correct sort of affinity for this to happen properly. I believe the copper oxide is also chosen because it works over a large temperature range. So you'll notice that with normal photochromic, even commercially made photochromic sunglasses, at very cold temperatures, they will not become clear very quickly. Like if you put it in your freezer, it may take months or weeks or something to become clear. Whereas at high temperatures, it works pretty well. And the copper oxide is responsible for reducing that temperature dependence. And then we have sodium nitrate. This is an oxidizing element. So when this breaks down in the high temperatures of the kiln, it releases oxygen gas. And this is important because there could be a fairly strong reducing environment in there, or there could be, and we don't want that to happen because if there's a reducing environment, our silver chloride, or while this is being formed, the silver actually might be reduced down to metallic silver before the glass is even done being formed. And you can actually see this in previous glass batches. I had a problem with little silver droplets being formed in the crucible. Obviously this is no good because we want that silver to stay in solution for it to give us this property. And then finally, I'm not sure if this is critical or not, I started adding sodium silico fluoride to some of these batches, and the winning batch actually did have a little bit of sodium silico fluoride. And the idea with this is that it provides a nucleation center for the silver chloride to form. So the trick with this heat treatment after making the glass is that we have these silver chloride atoms distributed throughout the glass. It's sort of like a photograph, but it needs to be clear in its clear state, so there can't be too many of these silver chloride atoms or molecules. So what we do is we heat treat the thing, and the silver chloride will want to aggregate into bigger chunks, and that way they can actually convert into metallic silver and give us this great photochromic property. So what we do is add some non-dissolvable stuff. These fluorides are apparently not dissolvable in the glass. They're still clear, but they're like little pellets sort of distributed throughout the glass, and they provide like a convenient source of condensing for these silver chloride atoms to start forming clumps. So if you're having problems getting the silver chloride to clump, you can add this and that will help out the process. If you don't want to add the fluorides, you have another option to create these nucleation centers. What you can do is just keep adding so much silver nitrate that eventually all the silver chloride that's going to form has formed, and then there's actually excess silver left over. And what will happen is the excess silver will just hang out in the glass, and so it actually starts out kind of dark. Basically, the silver provides its own nucleation centers. And this one is actually photochromic as well. The trick is that it just starts out kind of this reddish color because it's actually silver nanoparticles that are distributed throughout the glass, giving it this nice color actually. So if you want sunglasses that go from dark to really dark, this is the one for you. I forgot to mention that a lot of these ingredients are volatile at really high temperatures. So we're in the kiln at, 1200 degrees C. The silver is not just hanging out in there. The silver is actually evaporating away at 1200 degrees C. So to make matters even more difficult, after you've come up with this special formulation, if you were to put all these ingredients into one of those tiny melting dishes and left it there overnight at 1200 degrees C, you wouldn't have any silver in there left whatsoever, and your glass would not be photochromic. And so it's a really good balancing act, difficult balancing act, between getting the process set up correctly such that you put in enough ingredient and then cook it for long enough such that just the right amount of ingredient is left over at the end of this process. And it makes it very difficult if you're using small batches. So if you do this yourself, I would recommend using bigger melting containers than I am. So I'm making these like tiny, we're starting with 20 grams of borate. This whole glass ends up being about 20 grams because all this carbonate gets burned off. So we start with maybe 30 grams of ingredients or 30 something, and we end up with 20 grams of glass. That's really not very much, and the fact that the melting vessel has like a lot of surface area to it means that a lot of the silver is burning away. So you're basically talking about making a soda and then leaving it on the counter and waiting for it to go flat, but not too flat, and then stopping it at just the right point so that you have just the right amount of ingredients. And remember that the silver is going to volatilize at a different rate than the other things are. So if you're trying to control the ratio between silver and copper, for example, and the copper is not volatile or it's only a little bit volatile, and the silver is really volatile, then there's like this very narrow process window. And so it's a lot of tweaking, and I've made probably 50 batches of glass over the last few months, and found the process to be kind of fun, but also maybe a little frustrating. But I guess that is part of the fun of it. Oh, one last thing. How do you get these cool colors? These are all special oxides that can be added in really small quantities. And so this is actually copper oxide. So if you put in a lot more copper oxide than 2 milligrams, let's say you put in like actually 0.1 grams of solid, of pure copper oxide, you end up with glass that looks like this. This one is chromium. Chromium oxide is green. And also, interestingly, you can control the color of it based on its oxidation state. This deep blue one is copper oxide when it's oxidized as hard as you can. I think it's like 2+ maybe. And then this is also copper oxide that is neutral or even slightly reducing. So this might be like 1+ or something. And a lot of these oxides have 2 colors that you can get to with different oxidation states. Okay, well I hope that was helpful, and feel free to ask me any questions if you get into making glass, and I will see you next time. Bye!